this live session on computational fluid dynamics, where we solve problems based on the assignments that were given on the previous week and the non-graded assignments that were given this week, and also one example problem. Let's get started. So the first question of the previous week, and by previous week, this week's lectures include all the flow through triangular duct. And we see that from the lectures, we see that we solved that using something known as the finite volume method. So let's get started with the questions, the graded assignments. So firstly, we have to consider the figure that's given here. It's a right angle triangle, triangular duct, and we have to compute the steady laminar fully developed flow through the triangular duct shown in figure 1. So for this, what is the governing equation here? So for a fully developed steady laminar flow through a triangular pipe, we from the Navier-Stokes equation we actually balance the viscous pressure, viscous forces with the pressure forces, and for a fully developed laminar flow, we see that the pressure gradient dou P by dou X should be a constant. So therefore, the first option is wrong, and the second option, del dot del U, is a constant, is correct, and third option is again wrong, because there is a missing del dot del U should be equal to minus 1 by mu del P. Since that 1 by mu is not there, this third option is again wrong. Moving to the second question, for a steady, again this is for a steady laminar fully developed flow through a triangular duct shown in figure 1. Now, which of the following is the admissible form of the governing equation? We saw that the governing equation is given by del dot del U is equal to constant, is equal to minus 1 by mu dou P by, or minus 1 by mu del P. Now, what is seen here is that so we wish to compute the steady state laminar fully developed flow through a triangular duct as shown in this figure. And for this case, which is the following admissible, which of the following is an admissible governing equation? We saw from the previous question that del dot del U must be a constant for a fully developed flow, and it is also equal to minus 1 by mu del P. So for a fully developed flow, we can say that del dot del U is given by, is actually given by del dot del U for in is given by dou square U by dou X square plus dou square U by dou Y square, and for that to be constant, it has to be either a constant or is equal to minus 1 by mu dou P by dou X in X direction. Therefore, option 2 is correct, option 3 is wrong, option 1 again is wrong. Option 3 is wrong because here in the denominator is minus 1 by mu dou P by dou X. Moving to question number 3, for a steady laminar fully developed flow through a triangular duct, which of the following equations is applicable? We know that in order to for the mass conservation is given by the equation of continuity given by del dot u is equal to 0, so this equation is applicable, and we know that del p should be constant in general, but does not is not equal to exactly equal to 0, so this statement is wrong. And we know that del square p is the Laplacian is 0 since del p is a constant. Moving on to question number 4, we wish to solve the velocity profile for fully developed flow through the triangular duct as shown using the grid shown in the figure 2. We discretize the governing equations using finite volume method and obtain a set of algebraic equations. How many algebraic equations will we need to solve simultaneously if the wall has zero boundary conditions? Zero velocity boundary conditions. Now we know that the finite volume method uses the uh, velocity or generalized or it's the integral of the velocity in the entire segment that is being used, and in each segment there will be one equation that has been arised due to the discretization. So there will be 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10 segments present here. So the number of algebraic equations that we need to solve will be 10. Regardless of how the geometry of the uh, segment is, there will be 10 segments that we need to discretize, and we need to solve therefore 10 algebraic equations. Now again, for the grid shown in figure 2 as above, if the algebraic equations resulting from the discretization of the governing equations are arranged in the form of a matrix, then the non-zero coefficients in the coefficient matrix, option A will have a diagonal structure, option B will have a diagonal structure, option B have a tridiagonal structure with 3 adjacent diagonals including the main diagonal, option C have a pentadiagonal structure with 5 adjacent diagonals including the main diagonal, option D have a pentadiagonal structure with 0 diagonals in between some of the non-zero diagonals. When we discretize this equation and solve, what we finally get, the equation will not have a diagonal structure. If we try to discretize using the equations that were discussed in the class, and when we come to that, we will not be able to get a perfect diagonal structure. There will be a diagonal elements and there will be some off diagonal or diagonal elements. There will be a set of equations which will not have a particular structure, or which need not have a particular structure here. Now, question number 6, for the grid shown in figure 2. If the algebraic equations resulting from the discretization of the governing equations are arranged in the form of a matrix equation, the number of rows having exactly 3 non-zero coefficients in the matrix is. So basically, from each equation there will be from each interior equation there will be 1, 2, 3, 4, 5 equations, 5 variables, or 5 variables which need to be solved. But for the boundaries there won't be 5 variables, there will be so for when we discretize this equation in each segment, we will see that this segment has 1, 2 and 3 velocities that are associated with it. Similarly, this segment over here has 1, 2, 3 velocities associated with it. This segment here has 1, 2, 3 segments associated with it. So when we discretize these 3 particular segments, we'll have exactly 3 non-zero coefficients in the coefficient matrix. And when we discretize any other equation, we'll have to deal with either 5 or only one other element, or I guess only these two options would be there. So the correct answer is it will be exactly 3. 1, 2 and 3. Moving on to question number 7. For the grid shown in figure 2, if the algebraic equations resulting from the discretization of the governing equation are arranged in the form of a matrix equation, what do you expect from about the diagonal dominance? So, if the when the elements are arranged in the form of matrix, we will expect them to form a diagonally dominant solution, because these CFT solutions, when arranged, will be we are expected to form a diagonally dominant condition, and generally that is the case when we solve these equations. Even when we try to solve, when we actually solve and put it in a matrix form, we'll get in that manner only. Question number 8. If the shaded triangle in figure 3 is a right angled isosceles triangle, then the direction of cosines mx and ny of the vertical side are. So that let me take out the shaded area, and they have asked for the vertical side, and the vertical side, let's call this triangle as ABC, and the vertical side will have the unit vector over here. Therefore, its coordinates will be in the direction of its unit normal will be in the direction of -1, 0. Because the angle made by the unit vector around the plane is 180 degrees. So the coordinates will be cos pi, sine pi, and cos pi is -1, sine pi is 0. Therefore, the coordinates of the vertical side of the direction cosines of the vertical side is -1, 0. Then we can see that if the star triangle in figure 3 is a right angle isosceles triangle with vertical side of length A and a horizontal side of length B, then the direction cosines nx and ny of the diagonal side are, this is the important part, is given as the diagonal side. And for the diagonal side, what we see is that, suppose this is the diagonal side, this angle will be 45 degree, or let's call this as, this will be the unit normal, this will be the length B, this will be the length A. Therefore, cos theta, let's call this angle as theta, it will be B by root of A square plus B square. Since this forms a right triangle, this will be A square plus B square on the root. So cos theta will be B plus the root of A square plus B square. Sin theta will be A by square root of A square plus B square. So therefore option D is the correct answer. Question number 10. In deriving the set of algebraic equations for the grid shown in figure 3, boundary conditions are not used for how many cells? We see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 cells in total. And out of which boundary is shared by cell number 1, cell number 3, 5, 7, 12, 15, 16, 13 and 8. So there are in fact 9 cells that are in contact with the boundary. So it will be 1, 2, 3, 4, 5, 6, 7 cells that do not have a boundary condition. So the answer is C, option C, 7. So moving on to the non-graded assignments that were shown here in this week, which deals with equations associated with CFT techniques. We see that the first question is Newtonian fluid assumption is quite accurate for which among the following. And among the following, only crude oil is a new non-Newtonian fluid. Rest air, water, and diesel are Newtonian fluids. This is like a general knowledge question whether you know or not. There's nothing associated with this. Generally, organic oil solvents are usually supposed to be non-Newtonian in nature, especially high viscous oils. Then for the next question, for a Newtonian fluid, sigma Yy is given by. Basically, sigma Yy is actually minus P times delta Ij, or let's call, we change the coordinates over. Sigma Ij is generally P times delta Ij plus 2 mu plus tau Ij. And this sigma Ij is known as the total stress, and this is the pressure forces, and this would be from the viscous force stress. So when I write this sigma Ij as minus P delta Ij plus tau Ij, this tau Ij is usually 2 mu E Ij, and this E is usually given by dou Ui by dou J, dou Xj plus dou Uj by dou Xi. Sorry, half times this. So this would be given by minus P times delta Ij plus 2 mu into dou Ui by dou Xj plus dou Uj by dou Xi. If I equal to J equal to Y, then we'll get sigma Yy as minus P delta Yy plus 2 mu into, there will be a half here associated, that will get cancelled. So mu into dou, instead of writing dou Uy by dou Xy, I'll just write it as dou V by dou Y plus dou V by dou Y. And we know that delta Yy is actually the delta function, which is 1 if I is equal to J is equal to 0 if I is not equal to J. Here this one delta Yy, this is delta Ij. Therefore delta Yy will be is equal to 1. And for this given condition, sigma Yy is equal to minus P plus 2 mu dou V by dou Y. This is in fact the correct answer. Unfortunately, none of the answer matches with what we have derived, so the correct answer is none of the above. Moving on to the next question, the advection term in the momentum conservation equation in the x direction for constant property, two-dimensional the advection term in the momentum conservation equation in the x direction for a constant property two-dimensional Newtonian fluid can be written as. Basically what we have to write is the advection or the convection term is basically u, or let's just write as rho uu is del dot rho uu is what is being asked, and in the component balance we write it as u times dou u by dou x plus v times dou u by dou y plus w times dou u by dou z. And the only answer that matches with this is option A, u times dou u by dou x. Sorry, once again. Okay, I think I made a mistake while typing it out. One of the options would have to read it as u times dou u by dou x plus v times dou u by dou y. Not sure which option that I had to change, but one of the options is wrong here. It must be due to a typing error from my side. So the correct answer is u times dou u by dou x plus v times dou u by dou y in two dimension. I think that's option C is, this is, there is a mistake here. So option C should have been the correct answer over here. Then moving on to question number 4 in the non-graded assignment, the diffusion term is in the two-dimensional y momentum conservation equation. Actually, in the previous question, there is one small change I would make, is it should be multiplied times the density. But since they are just asked for the convection term, this density can be avoided, saying that density would come somewhere else in the equation. So correct term here would be the should be multiplied with the density. But yeah, this is also goes. Then the diffusion term in the two-dimension y momentum equation is given by, it's basically del square v, mu times del square u or vector v, and that is given by mu into dou square u by dou x square plus excuse me. So small mistake here. It's asked in the y momentum. So y momentum conservation equation. So it's mu into dou square v by dou x square plus dou square v by dou y square in two dimension. So option C would be the correct answer again. Dou square v by dou x square plus dou square v by dou y square. Option A would be the correct answer here. Basically, these all equations come from the Navier-Stokes equation, and that if we are able to simplify it, we'll be able to get these terms from that. Okay, if any of you who have joined the call now have any doubts, please let me know. I can discuss the questions once again. Okay, moving forward, we'll now do an example question as what we have been doing, where we consider the flow of water through a duct of a right triangle cross section of base 1 meter and altitude 1 meter as shown below. Now we have to segment it into 4 equal smaller right triangles and numerically compute the flow for a pressure gradient of 1 Newton meter using the finite volume method. So first we start with the governing equation given by the Navier-Stokes equation, which is given by rho into dou u by dou t plus rho u dot del u is equal to mu del square u. Let's just keep it as du by dt. So this is the substantial derivative, and we can get rid of this one. Mu del square u plus rho gx plus or here it will be minus del p. So when we solve this equation, we'll finally get the terms as mu del square u should be is equal to minus del p for a steady state two-dimensional equation. We'll get mu del square is equal to minus del p. Now in two dimension we can write it as mu into dou square u by dou x square plus dou square u by dou y square should be equal to minus dou p by dou x. Let us assume that this coordinate that's given is in the YZ direction and the flow is happening in the X plane. So mu into dou square u by dou x square plus dou square u by dou y square is equal to minus dou p by dou x is given here. Now it's given that the pressure gradient here is actually 1 Newton, and the fluid gets given here is of water. So viscosity will be equal to 0.001 in SI units, kilogram per meter second. So on the left side it will be dou square u by dou x square plus dou square u by dou y square should be equal to minus 1000. Now we need to discretize the domain into 4 segments as they have, as the question has been, given. And we need to solve each of these equations in these segments and then solve and find the answer here. So what we do is we see that there are 1, 2, 3, 4 segments, and therefore we'll be having 4 algebraic equations which needs to be solved. And as per the discussion that has been done in the the recorded lectures that have been uploaded in the Swayam website, we'll start by discretizing cell 1. We see that it is very much adjacent to let's call this as cell 2. And suppose this is cell 1, let us call this as cell 2. Now in order, just by considering the segment 1, we just define points 3 and 4 here, and we know that for a right triangle, for any kind of right triangle, usually the centroid happens at 1/3 of the length over here and over here. This can be obtained by the knowledge of using the coordinate system. If 0, 0, 1, 0 and 0, 1 are the coordinates, then the centroid formula is usually given by x1 plus x2 plus x3 by 3, comma y1 plus y2 plus y3 by 3. So this should be equal to 1 by 3, comma 1 by 3 from the axis where this is the origin. Similarly, if we are considering our cell 1 here, then we know that this distance has to be equal to 0.5. Since the entire length is 1, this distance has to be 0.5, and this distance will also be 0.5. Therefore, this centroid over here, let's call this as xc1, yc1, and there will be we would not want to know the midpoint over here. Let's call this as let's call the coordinates here as xm1 comma ym1, sorry, xm3 comma ym3, since this section is 3. Now we know that there is a cell over here, so there is a velocity condition over here, whereas for 3 and 4 it will be the ball boundary condition, whereas for 2 it will be the velocity at cell 2. So we'll define the centroid over here. We'll define the centroid over here, and that's at a particular distance of, let's call the coordinate as xc2 comma yc2, and the midpoint at the line at this 4 at the edge 4 is given by xm4 comma ym4. I'm just following the notations that were discussed in class. Let us consider this triangle to have a name as ABC. So when we try to discretize ABC, we first write the coordinates associated with each of this uh, each of these cells. So firstly we write what is xc1, we want to know what is yc1, then we want to know what is xc2 and yc2, then after that we want to know what is xm3 and ym3, similarly xm4 and ym4. So let's first consider xc1 and yc1. So if this whole distance is, if the whole length of AB is 0.5, and if the distance of the centroid from the from position, if the entire distance is 0.5 and the distance from this edge to here is one third of the total length, then the total distance would be equal to zero point 0.5 times 1 by 3 is equal to 1 by 6. Therefore, xc1 will be 1 by 6. Similarly, since the whole length here is 0.5 and this length is 1 by 3 times whatever this length is, the value of yc1 will also be 1 by 6. This is coming directly from the geometry of the system, where we try to solve, uh, where we try to find the coordinates of xc1, xc2, yc1 and yc2. Now we'll move forward to find out how xc2 can be calculated. We know that the entire distance from here to here is 0.5. We know that distance from here, let's say here to here, is 1 by 3. So what is this distance? That would be equal to, oh sorry, one second. This distance is 0.5 and this distance is 0.5 times 1 by 3. Therefore, this distance has to be 2 by 3 times 0.5. So this height for yc1 is given by 2 by 3 times 1 by 2 is equal to 2 by 6. Similarly, when we have to compute this xc2, we know that this entire length is 0.5. This length is 1 by 3 times 0.5. Therefore, this length has to be 2 by 3 times 0.5. Therefore, this length is again 2 by 6. Let's now calculate what is this value, what is xm3 and ym3. We know that from looking at the figure, ym3 is on the line AB, so therefore it's 0, and xm3 has to be the midpoint of the line AB, so it has to be 0.25. Since the whole line AB is 0.5, xm3 should be 0.25. In a similar way, we can also write xm4 to be 0, since this line AC is on the y-axis, and ym4 to be 0.25. I hope this table makes sense. Now that we have made this table, oh, excuse me. Now that we have made this table, we are ready to find out how to compute nx, ny and all those things. So as per the discussion that how to proceed? We'll have to write nx, ny, and we have to write dou u by, I've taken this as x. Okay, let me just change the notations in the previous equations where I have to use w everywhere. Let's assume that flow is in the xy direction. So flow is in the z direction. Just have a quick change of x and y since I've used x and y here. So we need to compute what is dou w by dou x and dou w by dou y along each of these three lines. The first line is given by AB, and the unit vector associated with this line AB is in the downward direction. So the normal in the x direction would be 0, the normal in the y direction would be having a sign of -1, and we can write dou w by dou x to be equal to, since this is cell 1, we have designed cell 2 to be here, cell 3 to be here, and cell 4 to be here. It will be w1 minus w3, or wait one second, it doesn't matter what dou w by dou x we are computing, because we know that nx times dou w by dou x is being computed, and which will in fact turn out to be 0 since nx is 0 here. But we need to compute what is dou w by dou y, and dou w by dou y means the difference between cell over here and the cell over here, the velocity of the cell over here. So it will be dou w1 minus w2 divided by yc1 minus yc2, and this is given by w1 minus w2, since we don't know what the w is, and we have computed what yc1 and yc2 is. So it's basically 1 by 6 minus 2 by 6 is equal to w1 minus w2 by minus 1 by 6. Next we move on to line BC, which is along the diagonal over here. So the outward normal from this direction, from the line BC, would be towards in this direction, and we know that since it's an isosceles right triangle, this angle would have to be 45 degree. Therefore nx in this direction and ny in this direction is given by cos 45 and sin 45 respectively, and cos 45 is 1 by square root of 2, sin 45 is 1 by square root of 2, and dou w by dou x would be between this cell and this cell over here. Oh, one second, I have made a mistake here. It's actually w1 minus w3. Wait, I think I have made a mistake somewhere. It's ym3, since it's along AB, which is given by w1 minus w3 divided by yc1 would be 1 by 6 minus ym3 should be 0. So this is w1 minus w3 by 1 by 6. And for BC it will be w1 minus w2 divided by yc1, xc1 minus xc2, which is equal to w1 minus w2 divided by xc1 is 1 by 6 and yc1 is 2 by 6. Therefore w1 minus w2 divided by minus 1 by 6. Similarly, writing for dou w by dou y, we'll get it as w1 minus w2 divided by yc1 minus yc2, which is w1 minus w2 divided by 1 by 6 minus 2 by 6, because yc1 here is 1 by 6 and yc2 here is 2 by 6. Therefore, w1 minus w2 divided by minus 1 by 6. Now finally for the third line CA, which is this vertical line over here, the unit normal is in this direction. Therefore, nx will have minus 1 and ny will be in 0, because this angle would be pi or 180 degrees. This angle would be 180 degrees and cos pi comma sin pi would be its coordinates. Therefore, it will be minus 1 comma 0. Similarly, we'll have to write dou w by dou x over here. So we know that w1 minus w4 will come, and w4 we know that it is 0. Similarly, we have also not written that for w3. w3 will also in fact turn out to be 0. So w1 minus 0 by xc1 minus xm4, and xm4 is 0 and xc1 is 1 by 6. So we'll get it as w1 by 1 by 6. And we don't have to compute this since ny dot dou w by dou y does not exist. So we have this also ready. Now all we need to do is we just need to summate over all I ni times dou w by dou xi, and this dou w by dou xa has to be multiplied or dot product and equated to the pressure gradient, the constant that we have written in earlier case where it's minus 1000 actually. So we just have to equate it to this times the area. So when we write that, when we do that, we'll get 0 times dou w by dou x plus minus 1 times w1 by 1 by 6 minus 1 by root 2 times w1 minus w2 by 1 by 6, that will be plus, and here to be a minus, plus 1 by root 2 times w1 minus w2 by minus 1 by 6 minus w1 by 1 by 6 plus 0 times dou w by dou y should be equal to is what we have said as minus 1000 times the area, and the area of ij is given by half times breadth times height is equal to 1 by 2 times the length and breadth are 0.5, so we'll get this as 0.125. Therefore we can rewrite this equation as minus 6, or we'll just write this as W1 times minus 6 minus 6 by square root 2 minus 6 by square root 2 minus 6 plus W2 times 6 by square root 2 plus 6 by square root 2 should be equal to 1 to minus 125. Finally we'll get this equation as W1 times minus 24, sorry, minus 12 minus 12 by square root 2 plus 12 by square root 2 W2 should be equal to minus 125. This is our first equation. Similarly, we have to derive equation 2, 3 and 4 from cells 2, 3 and 4. We'll continue to do that right now. We will continue to do that right now. So let us draw some dotted line over here. Let us take the cell 2. And in our figure, cell 2 is this inverted one. This is the only inverted right triangle here. So we'll take cell 2 here. This is cell 1. This is cell 3. And this would be cell 4. Okay, as I was mentioning, this is cell 2, this is cell 1, this is cell 4, this is cell 3. So if we take an algebraic equation over here, we'll be ending up with an equation which contains the velocity at each of these cells, W1, W2, W3 and W4. Let us try to find out what the equation is by again doing the same method. So in order to discretize this equation, this cell 2, we need the coordinates of the centroids at cell 2, at cell 4, at cell 1 and at cell 3. So we know already the coordinates at cell 1, xc1, yc1. We already know the coordinate at cell 2 given by xc2 and yc2. That won't change, and that is given by 1 by 6, 1 by 6 and 2 by 6, 2 by 6. Next, what we need is xc3 and yc3. Therefore, the cell 3 we have to consider now. We know that this much length is 0.5. So what is this length? And we know that this much length is 0.5, and we know that this much length is 1 by 3 times 0.5. So the total length for xc3, for computing xc3, will be given by 1 by 2 plus 1 by 3 times 1 by 2, which is equal to 1 by 2 plus 1 by 6 is equal to 4 by 6. So therefore this coordinate will be 4 by 6. Basically the length from here to here would be 4 by 6. Now since yc1 and yc3 are at the same level, we can directly write yc3 as 1 by 6. Now in order to find xc4 and yc4, we use the same logic we have used here. We know that this much length is 0.5. We know that this much length is 0.5. Therefore, this length should be equal to 1 by 3 times 0.5. Therefore, this length should be equal to 0.5 plus 1 by 3 times 0.5, which is again 4 by 6. And we know that YC4 and YC1, XC4 and XC1 are the same x distance, therefore it will be 1 by 6. Distance from here to here is always 1 by 6. Now that we know the coordinates x at cells 1, 2, 3 and 4, we move forward to find out the next set given by the unit vectors along that and try to compute the gradient at those points. Okay, let us consider cell 2 again. We'll call this as PQR. Consider cell PQR. We'll start with the base that is given by QR. We'll have to find Nx, Ny, dou W by dou X and dou W by dou Y. We know that the unit normal along the QR direction is in this direction. Therefore, the normal is in this direction. Therefore, theta is equal to 90 degree here. Therefore, cos theta will be 0 and sin theta will be 1. Therefore, Nx will be 0 and Ny will be 1. Now, dou W by dou X, we know that this is, this is the centroid over here. This will be the centroid over here. Now, the gradient will be across these two directions in the X direction. No, sorry, one second. We don't have to calculate what dou W by dou X is since Nx is already 0. So, it doesn't matter what dou W by dou X is. Whereas dou W by dou Y will be the gradient across these 2 points, these 2 centroids. Therefore, dou W by dou Y is given by W2 minus, that would be cell number 4, that will be W4 by YC2 minus YC4. And we know that W2 minus W4 by YC2 is given by 2 by 6 and YC4 is 4 by 6. So YC2 minus YC4 would be minus 2 by 6. Next we have the line RP, I think, yeah, RP. And for RP we see that the unit norm, oh excuse me, okay, I think I am, please hold on while I just get that back. Yeah, okay. Anyway, the unit normal along RP is in this direction, and we know that for this angle is actually 45 degrees since this length is 0.5 and this since this length is 0.5 and this length is 0.5. We know that if this is the unit vector, this angle should be equal to 45 degree. Therefore, this should be 180 plus 45, which is equal to 215 degree. So cosine in that direction will be yielding a value of 1 minus 1 by square root 2 and minus 1 by square root 2. because this should be the direction of nx and this should be direction of ny. So therefore nx and ny will be minus 1 by square root 2. Okay, so we need to compute what is dou w by dou x next. We know that there is a velocity associated with this cell and with this cell, and since we are talking about the line RP, we have to consider the gradient across these 2 points. So there will be a gradient across the x direction, there will be a gradient across the y direction. That is what we are trying to find out. So dou w by dou x is given by w2 minus this cell here, the number is 1 and this is 2. So w2 minus w1 divided by xc2 minus xc1. Similarly, the y coordinate will be w2 minus w1 by yc2 minus yc1. So we know that w2 minus w1 will remain as it is. w2 minus w1 will remain as it is, whereas xc2 minus xc1 will be 2 by 6 minus 1 by 6, which is 1 by 6. Similarly, w2 minus w1 will remain as it is over here, w2 minus w1 divided by yc2 minus yc1 will be 2 by 6 minus 1 by 6 will be again equal to 1 by 6. Now we have evaluated what happens across RP. We'll move on to what happens across the third line segment, that is given by PQ. And PQ is this vertical line that has a unit normal vector at the midpoint in this direction. And it is very straightforward that theta equal to 0 there, therefore nx should be 1 and ny should be 0. Because nx is cos theta, ny is sin theta, then nx would be cos 0, 1 and ny would be cos sin 0, which is 0. Similarly, in the same way, we compute w2 minus w1, sorry, it's not w1 here. It would be, we are dealing with cell 3 over here. So it would be w2 minus w3 by xc3, c2 minus xc3. Again, here it will be, here we don't have to compute because anyway, product with ny will render it to 0. Therefore, w2 minus w3 will remain as it is. xc2 minus xc3 will be, excuse me 1 second, visitor over here. So moving on, we were computing what is xc2 minus xc3. It's 2 by 6 minus 4 by 6, which is minus 2 by 6. Therefore, we have found the values of almost of all the values in the second cell. We'll write down what the second equation is. It will be just sigma, again same as ny dot dou w, ny summation of ni times dou w by dou xi. Therefore, it will be 1 times this value plus minus 1 by 2 times this plus minus 1 by root 2 times this plus 1 times this. 1, 2, 3, 4 equations will come out. So it will be w2 minus w4 by 1 by 6, sorry, minus 2 by 6 plus, or just write it as minus 1 by square root 2 times W2 minus W1 by 1 by 6 minus 1 by square root 2 times W2 minus W1 by 1 by 6 plus W2 minus W3 by minus 2 by 6 should be again the same as the value that has been previously obtained, that is C times the area, and C is minus 1000, area is 0.125, therefore this should be minus 125. Rewriting this, we can rewrite this as W1 times 6 by square root 2 plus 6 by square root 2 plus W2 times minus 3 minus 6 by square root 2 minus 6 by square root 2 minus 3 plus W3 times minus 3 plus W4 times minus 3 should be equal to minus 125. I hope that makes sense and you are able to get this answer. So finally we'll be able to rearrange this and write 12 by square root 2 W1 plus minus 6 minus 12 by square root 2 times W2 minus 3W3 minus 3W4 should be equal to minus 125. Now this will be our second equation. Next we'll move forward and try to discretize our cell 3, which is this cell over here. So this would be cell 3 and its neighboring cell is actually cell 2. This would be cell 2. Since cell 1 and cell 4 are not involved in this, we'll just call the point here as area 1 and here as area 4. And we know that area 4 deals with the boundary over there and area 1 will be deals with the boundary in here. So when we are dealing with the boundary, we take the midpoints here and here. When we are looking at the area, the velocity in the area, the cell 2, we are looking at the centroid over there. Therefore, what all do we need here? We need the coordinates xc3, yc3, xc2, yc2, xm4, ym4, and xm1, ym1. Please note that xc2 and xc2, yc2, xc3, yc3 will have the same values, whereas xm1 and ym1, xm4, ym4 will be different because this is for a new cell now. Let us call this triangle as xyz and try to compute what xc3 and yc3 was. We already found that xc3 yc3 is actually 4 by 6 comma 1 by 6. And xc2 yc2 also we have already found out, and it is given by 2 by 6 comma 2 by 6. Next, we need to find out what is xm1, ym1. By looking at the figure, we can easily identify that xm1 will have a value, ym1 will not have a value. Since this is the actual triangle, ym1 will be on this base. Therefore, ym1 will be 0, and xm1 is at the midpoint of this line. So this length is 0.5. Therefore, this length is 0.25. This from the origin over here, it will be 0.75. So this will have the coordinates 3 by 4 comma 0. Similarly, xm1 and xm4 will be in the same vertical line, since this is a right angle triangle. Therefore, xm4 comma ym4 will have a coordinate of 3 by 4 over here, and ym4 will have an elevation of half the total distance, since it will be bisecting over here. So it will be 1 by 4. Since the entire distance here is 0.5, this distance here will be 0.25. This is very basic geometry that has come up over here. So this is actually coming from the geometry only, all of these coordinates. If you have any doubts, please feel free to stop me, and I can repeat whatever that needs to be repeated. Okay, moving on, we'll have to now again go back and find out what the nx, ny, dou w by dou x, and dou w by dou y are. So we need to find out what is nx, ny, dou w by dou x, and dou w by dou y at each of these line segments xy, yz, and xz. Let's start with xy, whose normal is in this direction. So its x coordinate, it will have theta is equal to 270 degree, and for 270 degree we know that nx should be 0 and ny should be -1. It's basic computation that needs to be done over here. Therefore, we don't have to worry about dou w by dou x, we only have to worry about dou w by dou y. Now, dou w by dou y is given by w1 minus, this should be cell 3, so w3 minus, since it is at the wall that's being computed, it's 0 divided by xc3 minus y, this is not xc3, this is yc3 minus ym1. Now this is given by w3 divided by what is yc3 minus ym1? It would be yc 1 by 6 minus 0, which is nothing but 1 by 6. Next, we move on to line segment YZ, which is the diagonal over there. The diagonal will have a unit normal in this direction, and we know that this would be 45 degrees since it is an isosceles triangle. Therefore, the components would be cos 45 and sin 45, which is 1 by root 2 comma 1 by square root 2. If you have to calculate dou w by dou x, it's given by w3 minus, since it is along yz, we have to use the wall condition at the midpoint over here, so it should be w3 minus 0 divided by xc3 minus ym4. 4. Similarly, for dou w by dou y, we write it as w3 minus 0 by x. Sorry, this is not y over here. This will be xm4 here, and similarly, from the x here, it will be y here. yc3 minus ym4. And according to what we have already found out, xc3 is 4 by 6, xm4 is 3 by 4. So 4 by 6 minus 3 by 4 would have to be minus 1 by 12 if I am not wrong. Therefore, W3 by minus 1 by 12 would come here. Similarly, YC3 minus YM4 is being calculated, which is 1 by 6 minus 1 by 4. Again, would turn out to be 2 minus 3 by 12 minus 1 by 12. I hope this part is very clear and easy to understand. Again, if you need me to repeat anything, I am ready to repeat. If you need me to show you something that you need to have copied down, I can do that. Please let me know. Moving on to the third line segment given by Zx. We see that there is a gradient from here to here in the x and in the y, but we need not worry about what is happening along the y direction, mainly because the x, the unit normal in the x direction is in this way, so this would be 180 degree. This would be the 180 degree inclination. So we know that cos 180 is minus 1, sin 180 is 0, and dou w by dou x will be w3 minus w2, since this is cell number 3 and this is cell number 2. So wt3 minus w2 divided by xc3 minus xc2. Therefore, this should be w3 minus w2 divided by xc3 is 4 by 6 minus xc2 is 2 by 6, which should be 2 by 6. And we don't have to worry about what is there in over there. So we have almost computed the we can now compute what the algebraic equation arising from the discretization of cell 3 would come out to be. We will get that equation. If you are able to do it with me, I would appreciate it. But yeah, if you are able to find out yourself, well and good. So it will be minus 1 times w3 by 1 by 6. Therefore, it will be minus 6 w3. Then 1 by root 2 times this plus 1 by root 2 times this. So minus 12 by square root 2 times w3 minus 12 by square root 2 times w3. Then minus 1 times this. That would give us minus 3 times w3 minus w2. Again, the constant is minus 1000 times area is half times length times height, which would come out to be minus 125. Rearranging this, we'll get w2 times 3 is my plus w3 times minus 9 minus 24 by square root 2 should be equal to minus 125. basic rearrangement and substitution is what I have done here. Nothing too much complicated has happened till now. If you have any doubts, please feel free to stop me. So this would be our equation number 3. Next, we have 3 equations now. We have to solve for the 4th one on the top over here. Cell 4 is what we are going to solve now. We'll be taking the help of cell number 2 and this wall condition over here and this wall condition over there. Therefore, let me draw cell 4 first. So I guess this would be our cell 4. Just one second, let me just redraw this. Excuse me, this is coming out to be a very bad drawing over here. So this would be our cell 4. Our cell 2 is adjacent to this and is looking like this. So this would be cell 4, this would be cell 2. I'm calling this edge as 1 and this edge as 3. So therefore we would need to compute using the centroid over here xc4 yc4. Here it will be xc2 yc2. We would need the midpoint over here xm1 ym1. Here it will be xm3 ym3. So using these many points we'll be able to figure out what the equation stands for. Mr. Vinay Yadav, are you there on call?
Yes, I'm.
Are you able to follow what I am saying? Do I need to repeat anything?
No,
Or,
no, I am getting that. Yeah.
all right, wonderful. And Mr. Chandrasekhar, are you there? Okay. So let's find out what the coordinates xc 4 yc4 and we need xc2 yc2. We need xm1 ym1.
You will
Sorry?
do some coding also, or no?
No, I'm not going to do any
You will do
coding.
some coding?
I'm not going to do any coding
Okay,
right now.
manually.
I'll just
Okay,
solve this. I'll just be solving this using hand calculation or just
okay,
direct
okay,
solution, nothing else. Coding is not there as part of this course. For the entire course, you won't be required to do any coding.
okay,
And we need xm3 ym3. We already know what is xc4 and xc2 and yc4 yc2. Since this is a new edge, xm1 ym1 xm3 ym3 need to be found out. I'll just write down the values of xm4 and sorry xc2 yc2 is 2 by 6 2 by 6, xc4 yc4 is 1 by 6 4 by 6. So this should be 1 by 6 comma 4 by 6. This should be 2 by 6 comma 2 by 6. And xm1 would be since this is the entire triangle, this should be 0.5. This would be at the midpoint, so this should be 0.25. Therefore, this total length should be 0.75. So ym1 would be 3 by 4 and xm1, since it is on the y-axis, xm1 will be 0. Now xm3 will have the exact y coordinate over there, so 3 by 4 will remain as 3 by 4 and xm3 will be half of this distance. This is 0.5, therefore this would be 0.25. or 1 by 4. Now that we have the coordinates of all the points, we can move forward and find out what is, again, same as previous, we can find out what is okay. Back to nx ny dou w by dou x dou w by dou y. Now, since I also already used, I think I used ABC here, I've used PQR here, I've used XYZ here, so I think I have to go with something else now. I'll go with MN. We'll first deal with the base Mn, and the unit normal direction is in this direction. So Nx is 0, Ny is -1. Since the entire angle will be 270 degree, cos 270 is 0, sin 270 is -1. Dou w dou w by dou x, we don't have to worry about that. Dou w by dou y will be the velocities difference between these two places. So it will be w4 is over here and w2 is over here. So w4 minus w2 divided by yc4 minus yc2. Now w4 minus w2 divided by yc4 and yc2 is basically 4 by 6 and 2 by 6 respectively. So this value will come out to be 2 by 6. Next, we'll go to the diagonal side given by, I think, NO. This is the diagonal side. So we make use of the wall conditions over here to make sure that there is zero velocity over here. So first we need to find out what the unit normal is. Since this is the unit normal in this direction, this should be 45 degree. Therefore, both nx and ny will be cos 45. So this should, nx will be cos 45, ny will be sin 45. Both will be coming to 1 by square root 2. And dou w by dou x is given by w4 minus 0 by the corresponding terms, and it will be w4 minus 0 for the y term as well. So it will be w4 minus 0 by xc4 minus xm. I think the region is 3 here, so it's 3. Similarly, w4 minus 0 divided by x will be yc4 minus ym3, and xc4 is 1 by 6, xm3 is 1 by 4, so 1 by 6 minus 1 by 4 should be minus 1 by 12. So it will be w4 divided by minus 1 by 12. Similarly, yc4 minus ym3, yc 4 by 6 minus 3 by 4. So it will be 4 by 6 minus 3 by 4. It will again have the trigonometry. It will be 8 minus 9 is again minus 1 by 12. This will be again 4w4 by minus 1 by 12. Now we'll move on to the last side that needs to be evaluated. It is along OM. And along OM, it is the unit normal is in this direction. Therefore, nx will be minus 1, ny will be 0. and we'll get dou w and w4 minus 0 divided by xc4 minus, since this area is 1, we'll have to do with xm1. We don't have to worry about what is on the y, what is the gradient along the y direction. So we'll get this as w4 by xc4 minus xm1 will be xc4 minus xm1, 1 by 6 minus 0 will be 1 by 6. So we have this table as well. We'll be computing what the final equation is now. For that, all we have to do is multiply this with this, multiply this with this, multiply this with this, multiply this with this, and add all of these terms together. So we'll start by writing the first equation, which is minus 1 times w4 minus w2 by 2 by 6. That is minus 3 times w4 minus w2 plus 1 by root 2 times minus 12 by 4. So it's minus 12 by square root 2 times w4. Again, 1 by square root 2 times w4 by minus 1 by 12. So it's minus 12 by root 2 times w4. Then it will be minus 1 times w4 by 1 by 6. So it will be minus 6 w4. Again, we have to multiply the constant times the area. So we'll get the final equation as 3w2 plus w4 times minus 3 minus 9 minus 24 by square root 2 is equal to minus 125. I think this is the final fourth equation you are going to get. Now let us combine all the four equations. Let me write down all the four equations first. The first equation is given by this over here. I'll write it directly in the matrix form. Let's see if there is any confusion. So in the matrix form, I'll have the Ax is equal to B form, and I'll have the X matrix as W1, W2, W3, W4. I'll have the B matrix, since all the RHS is constant, everywhere it is minus 125. So I'll keep I'll write that down now. So the B will be minus 125, minus 125, minus 125, and minus 125. Now in order to write out the A matrix, I may have to refer and write. So see if you can write that on your own. It will be minus 12 by square root 2. And it will be 12 by square root 2 for W2. Be 0 for W3, 0 for W4. From equation 2, it will be 12 by square root 2 for W1. Minus 6 minus 12 by square root 2 for W2. Minus 3 and minus 3 for W3 and W4 respectively. From equation 3, we'll get W2 as 3. So W1 will be 0. And W3 as minus 9 minus 24 by square root 2. Minus 9 minus 24 by square root 2. 0. Similarly, for equation 4, it will be 0, 3, 0, minus 9 minus 24 by square root 2. Now we have this matrix and we have this this particular matrix and we have this particular vector. We can now easily find out what the values of W1, W2, W3 and W4 are. I request you to complete this in the next 10 minutes. I'm not going to do the calculations by myself. I am hoping that you would be able to do this simple calculations. I can compare the answer at the end of the class in 10 minutes. If you have any doubts, please let me know. I'll be around here. Uh, just excuse me for a couple of minutes. I'm just hitting someone on the door. In the YouTube video I'm uploading, I'm just showing a system of equations calculator that I'm getting from net. You may use that for solving the equations as well. Okay, I got the answer as the following: 11.81, 13.78, 6.4, and 6.4. Now that actually makes a lot of sense if you take a look at the geometry that was given for a right triangle system, such as sorry, the figure that is being shown here, and when we discretized it like so, and called 1, 2, 3, 4, and we saw that velocity is maximum along cell 2, and that is 13.78 meter per second. Segment 3 and 4 are identical and has 6.404, and the second highest velocity is when the channel has a rectangular duct over here, or represents something similar to a rectangular duct, and is 11.81 meter per second. Please verify the answers on your own, and let me know if I have made a mistake or somewhere. Yeah, so that is it for the class today. I sincerely thank you for your time and attention.